Okay, I've recently run this conjugate heat transfer case, so I'm just going to run through the setup. Initially in Snappy Hex Mesh, you specify 3 zones, and so you can view the zones by doing read zones and then selecting BTK composite, and then just expand the range. So we can see here we've got 3 zones, and it's just like a 2D case, so it's got a small thickness. And if we go to the snap to mesh, we can see what it looks like there. And if we want to view that a bit better, we can do decompose polyhedra, and that looks a bit nicer. So that's our 3 zones, and the way that is set up in Snappy Hex Mesh is, well, initially um, we've got in tri-surface, we've got 3 cylinders. So if we switch that off, we can see our 3 cylinders. And in Snappy Hex Mesh, what we've got is we're reading the 3 cylinders at the beginning, and then we've got feature refinement on them, surface-based refinement. So yeah, for cylinder 1, which is the outer one, we specify face zone, face type internal, and we give it a name solid 1, and say inside that geometry, and then we specify a point inside cylinder 1, and then we do the same for cylinder 2, and then we specify the level, specify internal, inside, then we specify another location for inside that. Cylinder 3 is the inner one, so we don't want any mesh on the inside of that. So that is basically all you have to do. A bit further down, we've got location in mesh, which is a point outside of the 3 cylinders. So basically, a point outside the 3 cylinders is like out here. Then the other 2 points that we've specified are there and there. So that's all you need to do really, to set up in as far as Snappy Hex is concerned. So get rid of that. What else do we need to do? Once you've done the meshing, you'll end up with these directories 1 and 2, and we can change them to 0 a bit later. And in my notes here, I've got, after you've done the mesh, you split mesh regions by cell zones. Default region name solid 0, so that means the outer zone is going to be called solid 0, and then the other 2 zones are already named. After we've got a result, we need to convert each of these regions into a BTK file. So we run foam to BTK on each of those regions, because it doesn't read directly into PowerView once you've got 3 separate regions. So this is the case that I've saved already. So in here, once you've split the mesh regions, split the mesh by region, you end up with 3 separate directories. And in each of those directories, you specify your boundary conditions, and you've got the mesh inside there. And so for solid 0, for example, the temperature, for Z min and Z max, I've got a 0 gradient. For the outer boundaries, with X min, X max, Y min, Y max, we can either specify 0 gradient or we can specify fixed values. So I've chosen to fix the temperature on the outer boundary. And then we've got a coupled boundary in between. And it's the same for each of the other ones as well. So if we go to solid 1, solid 2 is on the inside. So on the inside again, we've got We've got the coupled boundary here. And then on cylinder 3, which is the inner boundary, we've specified a heat flux of, well, here we specified 100,000 watts per meter squared. And so that's it really. It's quite straightforward. The only other hassle is that you have to, you end up with 3 separate directories for each zone here. So you need to go in there and then specify the properties, which is easy enough, just standard material properties. So I've specified 3 different metals for each of these zones. I specified copper on the inner ring, steel on the middle ring, and aluminium on the outer ring. And then the only other thing we need to do setting up this test case is ignore these ones. The other thing we need to do is duplicate the solution and schemes files. So this is standard. I think I took this from the CHT tutorial, but we're just using simple algorithm there, and these are just standard settings, so you can just copy those into each subdirectory. And so when you run it, it actually runs really quickly. So if I do chtMultiRegionFoam, if I use the PyFoam plot runner to do that. So when that runs, that'll show convergence. The first iteration takes a while, and then once it gets going, it speeds up quite fast. So we're only doing 1,000 iterations, and that's a lot more than we actually need for this test case. You can see that it converges nicely. It's only monitoring the temperature, and then after 300 and something, it flatlines anyway. So 400 would probably be enough for this case, but it's nice to know that it's converged. When that's ran, get all of this PyFoam rubbish, but we've got a solution in 1000. We can't read that. We can't read that directly into PowerView as far as I know. So I just use that command, and that converts VTK files. That gives us a VTK directory. And so this is just, let's get rid of the mesh from that on the geometry. So all I need to do then is go into VTK, load the outer region. So it's going from 300, which is what we set on the outside, to 307 on the inside. And I can also load the inner one and view that. So that's between 307 and 329. I can load the inner one, which is that tiny ring. Temperature on that is 329 to 330. That's the copper one. So yeah, we could change the range to view all of them. So if it goes between 300, 330.5, so that's our solution with the CHT through 3 different materials. And then in addition to that, I mean, we've only got the temperature there in the result, but in addition to that, we can look at recent plot over line, so we can have a look at the temperature through the solution. And to do that, we need to switch off the cell ID. So now we can see how the temperature changes in the in the outer region, and I'm going to change arc length to 0.0, which is x, and we can do that for each of the regions and just get a combined plot to have a look at the flows, the heat profile going through it. So that very briefly is how you do a CHT solution in OpenFoam.